And well, since I'm talking about linear logic, it's one of the laws that you have to talk about food or you get arrested by the linear police. And so I'm going to apologize if I make you hungry before lunch, but that's just what it is. Yeah, and so since we're having this summer school in America instead of in France, I'm going to be talking about how to come up with a menu for lunch, or a menu for an American lunch using linear logic. What's that? Baguettes. Well, and that's the story, right? Like everyone who introduces linear logic at some point talks about food, and you know a lot about where someone comes from based on what foods they pick. So that's pretty much it. Are you talking about croissants or pain au chocolat, or are you talking about burgers and fries? Right? What is it? So we're in America, so we're doing burgers and fries, because that's what you do here. Okay. So I'm going to tell you a story using linear logic, and it's going to be about a chef who's preparing for lunch. Okay, and so this chef, right, he works in a kitchen and he's got some ingredients, and he can make different things based on those ingredients, and he's putting together his menu for people coming in who want lunch. That's the idea. So, as a chef, right, I know how to make different things. One of the things I know how to make is that if I have beef and if I have a bun, I can make a hamburger. Right? That's something I could make as a chef. I know how to turn beef and bun into a hamburger. What else do I know how to make as a chef? Well, so here I'm trying to put together something that's the main plate of the lunch. Right? So what do you have with hamburgers? You have French fries, because that's what you have. And what do you need in order to make French fries? You need potatoes and you need oil, right? That's basically the two different ingredients. So if I have some potatoes, if I have a potato and I have some oil, I can make fries. It's something I can do. I can do both of these things. And I want to put together the main plate. And what is the plate? It contains both a hamburger on it and it contains some French fries. That's what the plate is. So the main dish is, and as a chef, right? So how do I make a main dish? What do I need? Well, I need all the ingredients for both of those things because I expect to put both of those on a plate. So if I've got beef, if I've got a bun, if I've got potato, and I've got oil, then I can make, well, let's just say burger. I can make a burger and fries. Burger and fries. I can do that as a chef because I'm clever and I can put two things on a plate. So the question is, why did I use this and not the other and? Right? It's a burger and fries. We have two symbols that mean and. Why did I use that one? Because the other one just doesn't work. Do you have a question?
Yeah, so what if I'm experimenting and I fried beef and came up with a new dish?
If you're experimenting and what was that, beef?
I took beef and oil and I came up with fried beef.
So yeah, this doesn't preclude us from doing other things. So I'm not sure. So is there something? I'm trying to think of an idea of something that you could make from beef and oil. What's a good thing you make from beef and oil? I don't know. Huh? Chicken fried steak. I like that one. Let's do that. So from beef, this is a good example. From beef and oil, I also know how to make chicken fried steak. Right? And from potato and bun, well, let's go. Basically, well, potato and bun, I don't know, it's some sort of potato sandwich. I don't know, this isn't a very good menu, but it's something I could make.
That's the only something that we have in the lunch here.
Yeah. Well, yeah, I'm trying to fry it as with oil somehow. So I would say you could make, like, some people make sandwiches out of French fries, but then you kind of want oil. But anyway, so again, if I had all of those things, beef, bun, potato, oil, I could also make a chicken fried steak with a potato sandwich. Sandwich. I could do that, so that's something else I could do. But potato sandwich sounds a little bit weird, so I guess I'm not going to do that. But it's not wrong, right? So I'm allowed to divide the ingredients however I want and make whatever I'm capable of making from it. So I could make lots of different things from the same ingredients. The real question is, why did I use times and not with? That's the real thing, and sort of the motivation here is, what's the difference of these things? Why are you just like making this stupid distinction? And it's because it's different, right? So times separates the environment. If I had used with, it would copy all of the ingredients into both things. So I would somehow have to make a burger out of beef, bun, potato, and oil. That's a little bit weird. And vice versa, I'd have to make fries out of beef, bun, potato, and oil. And that's not really what I'm doing, right? I want to track not just what's in my pantry, but what am I really using for every dish. So the reason you use times here is because you're really making both the burger and the fries at the same time and putting them together on the same dish. And therefore, I have to use all the ingredients for each of them. And the ingredients for the total is the ingredients for the each, right? You have to combine them. That's the idea here. Yep?
So we have some control for resources to not go, squandered, right? We want to make sure that...
Well, yes, and that was kind of done here, right? At the end of the day, in some sense, I can't say that I've got beef and potato, therefore I've got beef.
We don't want that.
You don't want that, and that's here.
The potato would be rotting.
Yeah, the potato would be rotting. So, because I didn't say, if I had said, maybe I've got more stuff, that's not linear logic anymore. That's why it's happening in those base cases. You're not allowed to drop something. You have to use it. So this is not linear logic, so we get rid of it, right? That's the idea. And that's sort of at the base case is what it is. Like in some sense, it's like, well, I'm given beef, so I've got exactly beef, and I'm given bun, and I've got exactly bun, and then I look up the recipe, which is something I have, and I do some kitchen magic, and I make them both, right? That's kind of the idea. So I'm not saying exactly how to get to that point, but once I've made both of those, I can put them together on a plate, and then the activity of me cooking that plate requires all of those resources, and exactly all of those resources. Right? Clearly, I can't make something if I don't have the ingredient, but I'm also not leaving ingredients unused and throwing them in the trash. Yeah?
What's the recipe that uses with?
What was the recipe?
Oh, could you make a recipe which uses with instead of times?
I'm going to cover all of them eventually, yes. Yeah, so I'm not, this isn't the only one. So I'll eventually get to all of the different connectives that we've seen so far. Well, not the constants, but the binary ones. Okay, so that is the, that's one part of lunch, but lunch isn't just going to be a main dish, there's going to be a few different things. Right, so I'm also going to have a soup, right? And I'm going to be like a typical restaurant and do a soup of the day. Which, when I write on the menu, I'm going to say, the menu is burger and fries and the soup of the day, which is typically one of two possibilities, right? Depending on what I've got, it's one of two different things. I'm either going to make chicken noodle soup or I'm going to make tomato soup. And what I make depends on what ingredients I happen to have in my pantry. Okay, so yeah, and that's the idea, right? So the soup of the day is the chef's choice, right? You don't come in and say, hello, chef, the soup of today is chicken noodle because, right, they're the boss, and they'll say, get out. That's the soup I have. I prepared it in the morning. You have to deal with that, right? So let's say for today that I happen to have, well, let's say in general, so these are the two things I know how to make. For here, I know how to make those. And let's say the recipes for those two things is that, well, if I have tomato and I have cream, then I know how to make soup. Those are the main ingredients for tomato soup. Right? And what else? Well, if I have, I guess chicken and noodle, then I can make chicken noodle. Chicken and noodle, then I could make noodle soup. Right? So I know how to make those two things. That's knowledge I have as a chef. But what resources do I really have? What's in my pantry? And so suppose today I've got tomatoes and creams, and I don't have chickens and noodles. What can I make? Well, I can't make the soup of the day. That is enough. I can make, from tomatoes and cream, I can make tomato. I can make either tomato soup, or I could make chicken noodle soup. Right? So I am capable of, and to keep it clear, that's the premise. Right? I do both of those things. What I'm actually going to do is make tomato soup as the soup of the day. So I'm capable of making the soup of the day because I only have the ingredients for one of the two soups. Right? So this is what the OR is for, is chef's choice. Right? Times is a combination plate, plus is chef's choice. Right? Yeah?
We don't have chicken.
We don't have chicken.
Or noodles.
We don't. But I can make the soup of the day. I don't need all of them to make the soup of the day.
Right.
And in fact, I would be wasteful because I'm only going to make one soup of the day. That's why it's the soup of the day. I don't make both.
That's true.
And this comes from the fact that, and that's why in the plus rule, right, to make the soup of the day, you only have one set of ingredients. You don't have the ingredients for both. You don't have to say what would it require to make the other thing, even though I'm not actually going to make that thing. Whereas for a combination plate, you do need all the ingredients because you're really, really making all the things and putting them together. And I have to actually make them in the real world. Yeah?
So the premise, the top part is saying my weakening is not so weak because I still know.
Well, yeah, and it's not weakening in the sense. Well, I guess it kind of is. I'm more vague here clearly.
Yeah.
But it's not.
Vague because you know which one.
It's not. Yeah. So.
In either, but you already know.
Yeah. So it's not so much. Let's just say, like, when we say linear logic has no weakening, it does not mean that an inference rule can't make something more vague. What it means is if there is a thing in your environment, gamma or delta, it cannot be dropped. You can't drop ingredients and throw them in the trash because then you're wasting money. But I can be more vague about it and call it the soup of the day and say no matter which day you show up on, it'll be one of those. And so you as the customer who is going to receive soup just has to be prepared to eat either tomato soup or chicken noodle soup. And you have to deal with what it is. That's just what it is. You don't have much choice in the matter. The chef says what it is, and you've got to be happy with it. Whereas in burger and fries, it's not like you do one or the other. You get both of these things. And from the customer side, right? Here from the customer side, you have to be prepared to eat either soup. Here from the customer side, you have to be prepared to eat both a burger and some fries. And you shouldn't leave either one on the table. You really need to eat both, or I will be very mad as a chef for you wasting my food and kick you out of the restaurant, right? So you as a customer, eat both. And you as a customer eat one, but you don't get to pick which one. The chef picks. That's the difference. And here there's no choice. The chef just makes both, and you just have to have both of them, right? And so in this case, the chef is the one making things to the right, and the customer would be using things to the left. Right, that's the idea. The customer's provided things. What's your question? It doesn't. So if I had other ingredients, I could make chicken soup. Hypothetically, that's something I know how to do. But in reality, I don't have the ingredients, so I cannot make chicken soup. I'm only capable of making tomato soup. But what I'm saying, I'm calling it the soup of the day, which is either tomato soup or chicken noodle soup. And so certainly, if I have tomatoes and cream, I'm capable of making the soup of the day. It just happens to be this one. On another day, if instead what I'm given is chickens and noodles, I can still make the soup of the day. It just comes out chicken noodle soup, right? So it's not that these are independent, and that's kind of the point. It's two independent possibilities, but the chef picks which one to do based on the resources they have. You're not really even deciding based on the resources. It's sort of like, if these are the resources you have, that's the one that you can make. Like, these happen to be mutually exclusive based on resources. But the point is that who gets to pick? It's the chef. The customer can't come in and order one of the two things. That's a difference, right? And so this is a mandatory two things for the customer, and that's a chef's choice. Yeah?
We are putting that information that whether the chef would be choosing or customer would be choosing.
Yes. And what was that?
Soup of the day is a name.
Yeah. So soup of the day is a proposition, which is tomato soup plus chicken noodle soup. So soup is one of those two things. And not sure if I'll have enough room there, but that's sort of the idea, is that, maybe what's going to go? Bye-bye for those now. Okay, so I'm building up my menu. So main, what's the main dish? I sort of just informally said it, but I can say the proposition representing the main dish is burger times fries. Burger times fries. And the soup, it's calling it soup of the day, but the soup is the chef's choice of tomato soup. Soup plus chicken noodle soup. Right? So here is me making the soup. Right? It so happens that because I looked at the way I made the soup, I know which one it happens to be. But when the customer walks in the door, they don't know ahead of time. They only learn once they sit down and start getting their meal. Okay? So what else? So this is going to be a 3-course meal, so there's also a dessert. So what's for dessert? And so this is going to be a little bit different. For dessert, I'm going to give the customer a choice, right? So as opposed to the for the day where the chef bosses you around, this is the other way where the customer gets to demand whatever they want off of the menu. And what are the two possibilities I'm going to give to the customer? So I'm going to say, well, it could be two things. You could either get a fruit salad or you could get a smoothie. And you get to pick, and so we have to figure out, so here I kind of told you what the connective is, but we have to figure out what connective models that. And so why am I able to give the customer a choice? Well, that's because both fruit salad and smoothie I can make with the same ingredients. If I have strawberries and bananas, I'm capable of making a fruit smoothie, or a fruit salad. And from strawberries and bananas, I can also make a smoothie, right? So if I have strawberries, and if I have bananas, then I know how to make a fruit salad. I just cut it all up and put it in a bowl. That was pretty easy. And also, I'm actually going to need more room. Let's rewrite that over here. So I've got strawberries and banana. I've got a fruit salad. And from strawberries and from banana, I've got a smoothie by putting it in a blender. Right, so both of those, right, I can make from the same ingredients. Right, it's do I cut it up, put it in a bowl, do I blend it all up together and put it in a glass? But it's really the same stuff. And therefore, you, the customer, gets to pick how you're eating strawberries and bananas. So what connective do I use in order to model this kind of choice, where I use the same stuff to make different things? So in that sense, I have both, yeah? Yeah, so that kind of looks like with, right? Because I use the same stuff to make different things, and I'm making them, so I want it on the right, and I want the environment to be shared, and there's two different possibilities. And if you just look at all the rules and try to like pattern match what fits this scenario, with is the one that fits. So here, this is a with, or at least I can apply the with on the right rule. This is a correct application, right? So convince yourself that this is a correct application. Banana entails fruit salad with smoothie. And so here, and this is another important lesson, is don't be too misled by the prose. That if I pronounce this as English word using the pronunciations over there, that might give you one impression, but the real thing is the definition. So don't just say, because I use these words, that's what it should be. Right? So that's the thing. So first, is this a correct application of the with on the right rule? So this is gamma. The rest of delta is empty, because I'm kind of only doing one thing at a time so far. And so I've copied the gamma in both premises. I've copied the empty delta in both premises. And then the main thing, the tau 1 is here, the tau 2 is here. So now I've got tau 1 with tau 2. So that looks like a correct application of that rule to me. So at least this is something that linear logic lets me say. And because the story kind of makes sense that I can make two different desserts from the same ingredients, and therefore I want to present to the customer the choice of those two things, I'm going to use with. So dessert is going to be fruit salad with smoothie, and so that is the customer picking between different options. Okay? So that's the three different the three different things. Right? And so what should the whole lunch be? Right? So there's two different things. Like first is what is a complete lunch and what are all of the ingredients I need to make a lunch? Right? So what is lunch? Lunch. If you come into my restaurant and ask for lunch, what do you get? So we had par and we had times. So here, well, let's think about the difference. So for times, is it kind of like burger and fries, which is I expect to receive on my table a combination of things, and that the chef prepares all of those things, or is it par, which we haven't seen yet? And I think times fits here, because just like burger and fries, me, the customer, gets both of those things. And as a lunch, I expect to get a main side, which I don't get to choose, and a dessert, which I do get to choose. Right? So here I'm going to use a times and say lunch is main times soup times dessert. And that's a lunch. And so intuitively, without getting bogged down by the logic, if I'm the chef, what do I need to prepare lunch? If someone walks in and they say, I want all three of these things, what ingredients do I need to prepare all three of those things? I need the ingredients from each individual part. Right? So here, the lunch or the ingredients for today at least, because remember, I could make two different soups, and that would be okay. But today it's tomato soup. That's the soup of the day I picked. So the ingredients for lunch, ingredients for lunch are going to be, well, pretty much you just combine them all. You combine the ingredients, because that's what tensor does, right? That's what times does. Is it just says you need everything all together. So the main required, well here, and I'll just say it's going to be the environment of all the things. That's my pantry. It is a list of beef, bun, potato, oil, what else? Tomato, cream, and, well, I don't need chicken. I only need one of the ingredients for the soups. Yeah, exactly. So and then strawberry and banana. So given that list of ingredients, I can make lunch for one person. And then here's the question of, what about this other thing? So the question is, could I use different ingredients to make lunch? And I could, which is instead of tomato and cream, I could use chickens and noodles and make chicken noodle soup. And that would also be lunch for the day. It's just today I happen to be using that one. So there may be multiple ingredients that you use, or that you may have different combinations of ingredients to prepare the same thing, because sometimes you're allowed to pick which thing you do, and therefore you only need the ingredients for one of those two options, whichever one you pick. So this isn't sort of exclusive. I could have ingredients prime, which is exactly the same thing, and the main idea here, right, is from ingredients. From ingredients, I can make lunch, and I do that by applying the tensor on the right rule twice, because there's two of them, and then you just follow what we did before. But I could also do that from ingredients prime, which is cross out tomato, write chicken, cross out cream, write noodles. I would also be able to do that. And it would be because I use the other, this was tensor right, this was plus right 1. I could have used plus right 2 for different ingredients, and then this one is with right. Okay? So, for one person, from the ingredients, I can make lunch for one person. Okay, but that's kind of a boring restaurant where exactly one person comes in and I make a single lunch for that one person. You know, that's maybe a little bit silly. So, hypothetically, I could also ingredients make, and I'll say it like this, lunch. I could make it again, in a sense, for someone else, and I'll say here that I can lunch par lunch. Okay, I'm serving lunch to 2 people. Or rather, so what's the missing step? So it's sort of like, what if I'm sending out 2 lunches to 2 different tables in a step? So this rule does not make sense. This isn't just the par and the right rule. So what if I had, oh sorry, I didn't list it twice, but what if I had this? Ingredients dot goes to lunch, comma lunch. So this, it's something I haven't shown yet, which is called mix. So in some sense, if I can do one thing and I could do some other thing, I could kind of do both things and they're just independent of one another, right? I can make lunch on 2 different stations. And those are just separate activities. And then I could combine all the resources together. So this, if we write the general rule called mix, looks like this. Gamma entails delta, gamma prime entails delta prime, gamma prime, delta prime. This is called mix. And I'll write it in parentheses because linear logic doesn't have to have that rule, and it's not really derived from any of the rules. But lots of things based on linear logic will have that. And if you take the analogy of resources, it kind of implies that this resources aren't a perfect analogy for what linear logic is really doing in the most basic level. But it does sort of suggest that maybe it's helpful to like build on top of linear logic and add some things. So mix is a perfectly reasonable thing to do, which is essentially if I can prepare 2 different meals, I can send them both out. And that's kind of where the in parallel is, right? 2 different servers go out and deliver 2 different meals, right, to 2 different people. Question?
That doesn't quite match with the judgment seems to work, because you said that only one of the things on the right really has to be true.
I didn't say only one has to be true. I said at least one is true.
At least one.
Yeah. So if from gamma I know at least delta is true, one thing in delta is true, maybe more.
Yeah.
And if from in delta prime is true, I know at least one thing in delta is true here, and at least one thing in delta prime isn't true there. So that's okay. Right? So from just that meaning, right? It's at least one, not exactly one.
All right. Oh, it's okay. Well,
Yeah.
But I mean, the analogy still seems to start to break down, though, because now I only have to serve one person lunch.
Right. Well, here it's sort of like I'm doing 2 things. Right? I've got 2 things on the right. So you could combine this together with the par on the right. So this now matches par on the right. Par on the right, and I combine that together. That's sort of 2 lunches in parallel is the idea. But you can only do this if you have the extra rule, which kind of makes sense for a restaurant. Maybe doesn't make sense in some other setting. But so really, it's actually for a lot of the analogies, it's kind of hard to come up with a use case for par. So mix says I could do that. So if mix makes sense for my scenario, which is if I can do 2 independent processes in parallel to one another, and then just combine them together in the same kitchen, then mix makes sense. And if I'm capable of doing that, then I could say that that represents a par. Yeah? Yeah? You're allowed to have more than one thing be true on the right-hand side. That's what I'm saying. It's not exactly one on the right-hand side. It depends on what you mean by resources. And so in some sense, usually the resources on the left are things you are given, and the resources on the right are obligations you must meet. So it's a little bit different from, say, like a classical logic, which is like 1 or more, I don't care. Picky than that, where in some sense I am meeting multiple obligations. But it's kind of a disjunction because there's some amount of like jumping. When you look in really the programming language view of this is that multiple things are the right are multiple continuations or multiple exit points. And the right is behaving what? Yes. So, and that's, I think, really why the intuition breaks down is, and we'll see in the afternoon, that if you're just doing like lambda calculus or intuitionistic logic, par just doesn't make sense because par only makes sense when I have more than one thing on the right, and that goes against the usual scenario in intuitionistic logic. Intuitionistic logic, we think of, I hypothetically have multiple premises and one result, and how could I have more than one result if I only have one result? Right? And so that's kind of why the intuition for par usually always breaks down. I'm trying to give a story where par makes sense, but it is a little bit tricky, and most people don't really use par in the relationship with programming languages for that reason. They usually just throw it out and don't consider it. Yep.
So I noticed that in your definition on the right, you have primes.
Sorry, they're commas that are low. They're not. So there should be no primes here.
Sorry, the mix.
In the mix.
Oh, yeah. So in the mix, well, because they're different resources, right? So.
But in the analogy example, there are not primes, right? It looks like the same
So because, and it's the same thing.
I'm just wondering if there's a semantic difference there.
So primes doesn't mean that gamma has to be different from gamma prime. It could be an identical gamma.
The whole point.
But then that just means I have multiple things. So, for example,
It's like concrete versus abstract, or like class versus instance, right? Well, linear logic is we're basically using instances, right? Different sets of concrete ingredients between two different functions, right?
not necessarily. That's just one application you might do, and then maybe you say that I can only join two environments when they're distinct. But linear logic makes no such distinction. So for example, right, so from another example is from $1, I can get a coffee, and from $1, I can get a coffee. And then so from $2, I can get 2 coffees, because I'm getting it for 2 people. That's okay. Nothing says I can't have dollar appear more than once.
So how does the
So this is 1, this is 1, and then it appears twice.
I guess I'm just not seeing, like, for introducing the same premise multiple times. What
Yes.
are we actually introducing?
So the difference between $1 and $2.
Right, so that's what I was saying about concrete. So then I would
Somewhat, but
concrete dollars and get $A and $A.
so it is an instance of $1, and here's another instance of $1. And those are both instances of dollars, and they are different. That doesn't mean I have to call one Jim and one Phyllis, right? So they can both be the same kind of thing. The propositions are the type of thing we're talking about, but you can have multiple instances of the same type of thing running around. I can have a herd of cats running around the room, and they are all cats.
So then why did we bother with the prime?
Because we care about the amount, and they might be different. So gamma could hypothetically equal gamma prime. There is nothing wrong with that. Gamma is not required to be exactly the same thing as gamma prime. And in fact, they might share a few things, but not everything. So really, it's just I need all of whatever was in gamma and all of whatever was in gamma prime, no matter if there is overlap, right? You know, maybe someone has, you know, a cat and a dog, and someone else has a cat and a parrot, and if you bring them together, you'll have 2 cats. That's okay. Or maybe just 2 people both have a cat, and when they come together, they have 2 cats. That's also okay. But they're both cat. We're not like naming them different things. We're not talking about locations. Aren't propositions. Propositions are types, and locations are sort of below types. Yeah. Yes.
The others may be false, right?
The others might be false.
So like well, let's say we go back into the with right rule at the above.
Mm-hmm.
Like for both tau 1 and tau 1 or tau 2 may be false because like some other thing.
Yes.
Delta 1 or delta 2.
So if it happens that the reason why the one premise is that tau 1 is true, and that the reason why the other premise is that tau 2 is true, then the conclusion makes sense because tau 1 and tau 2 are true. If the reason instead is anything else in either case, then it's still true down there because something in delta had to be true, so that's good enough.
But let's say like in only and something in delta.
Then something in delta is true, so the conclusion's still true. Yeah. Yeah, that's kind of the reasoning you do. And so, so for the first cut, for reasoning about these, it's easier to just say all of the environments are empty. And those are special cases of all of these rules. Like gamma might be empty, that's fine. Delta might be empty, that's fine. And then think to yourself, in that case, does it make sense? It's a lot easier. There's less like, well, what if this or what if that, and all of these different combinations. If that makes sense, adding a generic gamma and delta doesn't really break stuff. Yeah. And that's sort of the kind of the same thing as cut, which is if you just think about one thing, everything else is along for the ride, and as long as cut makes sense, you can always stitch it all back together again. Yeah, so the fact that cut makes sense, which is that, if you can produce something and consume something, means that it makes sense to sort of, well, what if it's this, but then what if this other thing? And that's that logic done in general. Yeah. Yeah.
So you know this coffee example. So how is this different from mix? Like you use the
oh, yeah, I guess you could also do mix, right? And then you're just sending out 2 coffees, right? So mix is different because it's not introducing a connective. This one is introducing a connective. I mean, that's just different things, right? I'm making a new proposition. Yeah.
So maybe I didn't understand the meaning of part in that case, but
Yeah.
just had its ingredient. Probably I would serve because
yeah.
think of one.
Yeah.
Is that far below that, trying to make sure that both lunches are delivered?
Well, I'm just grouping it together into a single, like what happens when 2 customers get lunch. I want to send out 2 lunches. So I'm just writing that as a proposition rather than as a list of stuff. Because they're the same thing on the right, I'm kind of just illustrating what is the point of par, is it lets you say what's a lunch for 2 people. You've got mix, of course.
So the par will kind of make and for both. Are you saying that? Like both?
Somewhat, right? I'm sending out 2 lunches. Right? I'm the kitchen. The kitchen sends out 2 plates of lunches to 2 different places. 2 different tables. That's the idea there.
The mix says you could send out just 1 lunch, right?
Well, so the mix says essentially that the servers can go to 2 different places and they don't have to talk to each other in parallel. And that's sort of a prerequisite of doing that, right? So yeah. So I mean, the difference of an environment and a proposition are an important thing to understand. It's the same thing. Do I have 2 free variables? Do I have 1 free variable that's a pair? I mean, they're kind of the same, but they're different because I write a different program in either case, right? It's like I just write a different program. And so there is a conversion, and it's sort of, maybe that conversion in and of itself is not that earth-shattering, but it matters and you have to deal with it. Yeah. Okay, so so I think I'm going to put these example aside to sort of finish off the discussion on linear logic, because people might be a little bit hungry now that we've been talking about food.
There is a long line.
Huh?
I bet there is a long line.
Oh, of course. Yeah. I want to go on to a much more interesting topic, which is, the symmetry and duality, because when you look at these things, man, they look really symmetric to me. That this is that just flipped around. This is that just flipped around. So shouldn't we say something about that? And what do we say about that? So the idea here is to introduce a negation to the linear logic. But it's going to be a kind of different thing. So all the stuff over there are connectives, right? Which means they are symbols that appear inside of a proposition, right? They're concrete syntax. The negation, the way I'm going to do negation, is not going to be a connective. It's going to be an operation on propositions. Kind of like substitution was an operation that took one proposition and gave me a new one, or took one expression and gave me a new one, right? So this is an active operation that modifies things that might be true or false. It is not a syntactic connective that appears in a proposition. Okay, that's an important distinction to make. And just to be extra confusing, Girard wrote it this way. So I'm going to write it this way because if you ever look up linear logic, this is probably what you're going to see, and it's going to be massively confusing. But the way he wrote negation was like this tau 2. And then you put a bottom as a superscript because, I don't know, that's where he came up with that. I think it has some justification in math somewhere, and I forget exactly where that convention comes from. But the idea here is you could think, what is the opposite of tau 1 with tau 2? And the definition, so I'm going to define negation as an operation. How? By induction on the propositions I have. Right? So consider what's the case for each connective symbol, and then say what it is. And the rules, the laws that are defining it, are actually not too bad. We're just doing what are the De Morgan laws for negation, right? How does that interact with conjunction, right? If I have an and of two things, if I negate that, I get an or of the two negations, right? So that's all we're going to do. The tricky bit is that because I have two ands and two ors, I have to pick the right one so that this makes sense. So what really is the mirror image of with? And it's going to be one of the two disjunctions, but which one? Is it going to be par, or is it going to be plus? And well, you might say par is like an ampersand, so why not that one? That looks like the appropriate one. Does anyone say that?
I'll say it.
Okay, you'll say that. But, well, you could say that, but it's not really what you want, because you won't get the nice, cool theorem if you do it that way. Right? So this one is the mirror image of with. And so that's what negation is saying. What's the mirror image of this thing? And so what you say is that with gets turned into a plus. And then we say tau 1 negate and tau 2 negate. So that's the definition of negation. And then you just keep going and you look at what is the mirror image of some other thing. And of course, the other way, if I have a plus, that gets flipped back into a with. Right? So that's the other side of this. And I have tau 1 negation with tau 2 negation. Okay? So those are the two sides. And as they are mirror images, they both just go back and forth. That's what this negation operation does. What else? What happens if I had the other sort of conjunction? What would that do? Tau 2. That's the other sort of disjunction, probably. And they are, remember, they're mirror images of one another. So I'll write that. Tau 1 negated par tau 2 negated. And if you encounter a par and you want to negate that, it goes the other way, right? So these are reversible. They reverse each other. Tau 1, 2 is tau 1 negated times tau 2 negated. Okay, and what else? Well, I've also got constant. I should say what those do. It's pretty much the same thing, right? The negation of truth is false, and the negation of false is truth, but it matters. Was remember, what was it? The two different business plans. One of them was someone who, what was it? Who promises to do nothing and wants everything, and so everyone ignores them, versus someone who promises to do nothing but wants nothing. Right? So it kind of matters. It was the two different falsehoods. So no surprise there that the nullary version of with gets turned into 0, and the nullary version of 0, or which is the nullary version of plus, and then vice versa. And then if I have 1, the opposite of 1 is bottom, and the opposite of bottom is 1. So here I've written some operations that just flip back and forth, and they're basically just De Morgan, and that's of course what negation does. But there's kind of a neat thing here, right? So first of all is, well, they usually call it involutive, but essentially is, right, tau the same thing as tau, not tau, right? So, well, theorem, question mark, is it the case that tau is somehow related to tau not, they're the same thing, right? So if I modify tau and flip it, and then I flip it back again, I get exactly the same proposition. So it's not sort of like, well, I can convert one into the other, or I convert it backwards. They are the same proposition. They have to be the same thing in terms of provability, right? Because, it's not just that I can convert between them. They are syntactically the same proposition. Okay? And so that is a theorem, and you prove it by induction on the structure of a proposition. And the proof is yes in every case. Like, it just flips back and forth. I go from here to here, and then back, and then apply the inductive hypothesis. And that's all you do in every single case. So why is that interesting? Can anyone tell me why that might be interesting? You have an idea? Yeah?
Well, in constructive logic, we don't have double negation.
Right? And that's what a lot of people say, right? If it's constructive, there is no double negation. But linear logic is like a subset, more or less, of intuitionistic logic, right? In that, at least this stuff, the main difference is that it's sort of like intuitionistic logic, but then weaker, right? Sort of like intuitionistic logic is classical logic, but I remove some proofs. Linear logic is, you can think of as intuitionistic logic, but I remove some proofs which are duplicating facts or assumptions, right? So you do have it. So it's kind of like both a restricted version, more expressive. And the main difference is that intuitionistic logic cannot express negation in this way. Instead, they would say, oh, I've got a connective for negation, right? Not tau, which is really, they usually define as tau implies 0 or some void thing. And that's just a different thing. And there's no reason to think that tau arrow void is the same thing as tau. This is a different sort of negation. And so it's sort of like in intuitionistic logic, you can't talk about the linear negation. And that's why it's different. Other question?
This opposite corresponds to what I call non-tau.
Right.
Like if we have tau and not tau on the left side,
Yeah.
can we prove 0 or 1?
Yeah, so that's the question, is what's the other relation? And so, well, I'll kind of get into essentially the last missing piece, because I did linear logic in a sort of way that's not super traditional, because that's even harder to follow, basically. So I'm just going to start erasing some of the rules now, but there's another theorem that is true that should at least hopefully convince us that it does make sense, which is a duality theorem, which is that if gamma delta is derivable, then delta naught entails gamma naught is 2. Okay, and by that I just mean apply the negation operation to everything in gamma and delta. Right, that's the definition of that. And at least, kind of briefly convince yourselves that this makes sense, which is, again, sort of by induction, and, well, I can flip par and I get tensor, I can flip plus and I get width, and the rules match up, right? They were sort of the mirror image, right? So this is true. And this sort of suggests that having a not tau, or a tau on one side, should be the same thing as having not tau on the other side, right? And that's kind of like the last missing rule, which is how do I invert and go back and forth? So the inversion between the two sides of entailment is that if I on the left, then I've got tau on the right, right? Because they're sort of the same, right? instead of doing this flipping globally, can I just flip one thing? And I'll make that a rule of the system. So this is inversion on the left, and then have an inversion on the right. So if I make a tau, and that's the same thing as using a tau, inversion on the right. And so that's sort of that you'll need for at least this part of linear logic I've shown. And if you look at the presentation of linear logic, you usually won't see this rule. Why is that? Because, right? So they sort of pre-done this rule as much as possible because we're trying to cut down stuff we have to do. And that's like even harder to read because there's this implicit negation all over the place. But essentially, if this makes sense, then I can always take everything in gamma, shove it to the right. It's just the knot of all of those things. That's kind of the idea, which is very classical in feeling, which is that A implies B is kind of the same thing as not A or B. And that kind of mixes with that feeling. And so usually, it's very common in linear logic to just see the sequence be left as empty, right as a bunch of stuff. And then to get that to work, you would write different rules for axiom and cut. So that's called a one-sided system because everything's all on one side. And if you read the literature, you'll probably run into it if you really dig into linear logic. But this is the two-sided version, kind of how you undo all of that shorthand. And so their identity looks like this. Instead of saying tau implies tau, which makes sense, you say or not tau. So that's identity. And then cut looks like this. If I've got a tau in delta, and if I've got a not tau in delta, then, delta prime, then I've just got delta prime. And so these are fancier rules because we're applying an operation, right? So I won't actually see not tau. I'll see whatever the result of not tau is and then kind of have to match them up, like, is this the negation of that? So you'll see this all the time in the literature. I did not introduce this because I find it harder to read. And I think a lot of people find that harder to read, but it does let you cut down the rules. If you do that, you only ever need to write the right rules. You don't have to do the mirror image on the left. So it lets you cut down on the stuff that you do. But it's a bit harder to read. Okay, so that's that. And so, so one question is this now with these rules, is this negation? If I have that tau is true and also not tau is true, can I derive the empty sequence or something like that? Or can I derive 0? Or something. What's that look like? Okay, and so, what's one thing I can say? I can say here that tau implies tau. That's the identity rule, right? And then that means by applying inversion that tau and not tau implies empty, an empty sequence. Inversion on the left. Right? So if I have both tau and not tau, I get nothing, right? They sort of cancel out and annihilate each other. And vice versa. This one, right, sort of the other way. Right? Either tau or tau, not tau, have to be true. Okay, this may seem a little bit goofy, but why is it interesting? Well, because it lets you represent or break down implication, linear implication, in terms of these connectives. Right? So in classical logic as well, you can break down implication. You don't have to really think about it because it's some combination of not and or. And it's the same idea here. So what is the sort of thing that's like implication? And sort of one reason why you can't do that in intuitionistic logic is because, well, it's the wrong not and it's the wrong or. Right? So what's the or that you want? And so I'll do it this way. In some sense, I want to be able to prove that, tau implies tau is true. I want to say that if I know that tau implies tau, and implication is written that way, usually that's a linear, very sensitive about the inputs. Okay, and then, so then I sort of expect to do something like this. So this is the identity, and this is what you might think of with the linear rule on the right. So this looks kind of just like lambda calculus or implication, right? It's, well, to do an implication, just assume the input, show the output, and they're the same, so no problem, right? And so the difference here, so how do I break that down? And you can do that with negation and par. Right, so I'll do the same sort of proof. Here, tau, I'll say not tau, par tau. I've got nothing here. Into not tau, comma tau. So this is the par on the right rule. And then use inversion, move that to the other side. All right, so this would be tau not entails tau. So this was the inversion rule. And that's now an identity. Why? Because double negation, in the way I've defined it, is clearly a syntactic identity. It gives, if I negate something, negate it again, I get back an identical proposition. So that works. So this is why in linear logic, many times they don't take implication in this form of linear logic. Implication is not a given. They'll say that tau1 linearly implies, or some people say lollipop, because that's kind of what it looks like. And you have to be hungry when you're doing linear logic. So tau1 mapped to tau2 is sometimes and often tau2. Right, so it's kind of that thing. And you can kind of see, oh, well, those proofs were the same, like the identity function. And the reason why this isn't totally bogus from a constructive point of view is that here I'm obligated to provide something to tau2 at the end of the day, because really I have to provide something for both. Right? And providing to a negation is like assuming an input. Right? And sort of the other way that you might read it is you could say that tau, well, and using this encoding, it's the same thing. Tau1, tau2 is, or tau1 par tau2 is the negation. So the kind of confusing par is sort of because really what it's trying to do is some sort of implication-y thing, but in an asymmetric way. Whereas implication is very asymmetric. I assume the one side, I prove the other side. Those are very different activities, whereas par, they're the same sort of activity. And you could encode that as sort of flipping that role reversal on your input or on your output. So we're at 12:12. I think I'll wrap this up now after a couple questions, then we'll go to lunch. Yeah? Oh, sorry, that's a typo. It's probably because I wrote a tau and that looks a lot like top to me. Yeah. Yeah, sorry, they should all be, if there's a superscript here, all the superscripts should be bottom, which is an unfortunate, like using the same symbol again for a very different thing, but I mean, that's kind of just what it is in the literature, so it's better to sort of know what's out there than to invent a totally different thing. Yeah, question?
This still feels kind of different from negation or classical logic because their negation is an actual...
Yes, exactly. Exactly. And there are different reasons for them. Some may be technical, some not. But one of the many motivations for linear logic is to have a case where at least the propositions tau and not tau are like the same sort of thing. And well, as a design, if that's your design goal, one way to go about it is to say they are exactly the same thing, and therefore my system only makes sense if that's what it is, right? That's kind of, you can think, if that's an objective, let's just put that really deep into the system so that there's no way around this problem. So that's one reason. And then, so you could also, on the other hand, you could have a connective that does negation, and these would be rules. So that's sort of wrong. The other reason is because linear logicians love one-sided. And this doesn't make sense if it's a connective, but it does make sense if it's a sort of operation and then you check, well, I've only got two things. Does it just so happen that they're opposites of one another? Right? And if you don't have that, then the system doesn't make sense. So if you want to do the one-sided trick, this is a requirement, but it can also be kind of like, you know, design aspiration, in a sense. Yeah?
Is the negation of a resource just like an emptiness or like a debt?
Is the negation of a resource emptiness or debt?
Yeah.
Oh.
Rather like have empty
Yeah.
shelves at the grocery store, or the
Yeah.
grocery store owes the other grocery store like 100 apples.
Yeah, kind of. And it's sort of like that.
Or like debt.
Well, yeah, kind of. It's debt. Yeah, or yeah, I have the opposite of that, right? It's like you could say, you know, I have a debt, or I owe the bank $1, which is the opposite of having $1. And if I merge two accounts, one of them has $1 and one has a debt of $1, they cancel each other out. Right? They get back to zero balance, and that's kind of the idea there. Yeah. It's sort of like, how do you go the other way? Yeah. Okay, and it's kind of like if I have a thing that's different than wanting the thing, right? The emptiness of that thing, or the lack of that thing. And that's kind of what is going on. All right, so let's break there and then resume after lunch.